Okay, so let's start. So to give you a complete overview of kind of where we're at now, first lecture we introduced biomaterials. We kind of haven't got to that stage yet of applying the biomaterials. That's in the second half after your first midterm exam here. But what we have done is we've analyzed the properties of polymers. We've assessed hydrogen bonding. We've assessed different characteristics in the backbone that contribute to the TG and the TM. We know now how to get our polymers into solution, so like dissolves like, in order to make these number average molecular weights, or sorry, just general molecular weight measurements. So we know that we can make those now. The next step is going into looking at how we can characterize the TG and the melting temperature, and also the mechanical properties of the polymers themselves, using things such as tensile testing and dynamic mechanical analysis. So what we're doing is that we're slowly building up our understanding of polymers to apply them at the back end, right? That is the ultimate goal of this course, is that by the end, you should be able to suggest a polymer you can use in a particular application because of all the properties and all the different characteristics that we go through in the first half of this course. Now, Friday, we will have an in-class assignment. The in-class assignment is not going to take you as long as the previous in-class assignment. I've shortened it down slightly. That will be open book, and you can work in groups again. Again, it's just to check that you're reading the notes and you understand what's going on. Then you'll also have a homework assignment, which will also be set on Friday. That will have a week. Again, that is shorter than your original homework assignment in there. I've done that really just to, again, test some of the, applying some of the knowledge that you've learned in the class to solving some problems. And then after we have finished going over the mechanical properties, so today we'll go through the thermal properties. After we've gone through the mechanical properties, then you'll have time to do the midterm exam. I'm still working on ways to set that up, but for now, that will take place during one of the lecture times. So you'll have 50 minutes to complete that midterm exam. I will do a lecture where I'll go through the things that you should know for it and the things you should familiarize yourself with. But it's a good chance now to start compiling some of your revision notes as well, and making sure you understand things. My current office hours are underutilized. I think I maybe get one person per hour, which means it's good for that one person because I talk to them. Well, probably not good. I talk to them for a whole hour. But please start using those office hours, because as it gets towards the midterms, you know that it's going to get busier and busier, and it's going to get harder to get in the room. Now, I have done it before, where we've had multiple people in the room that are asking multiple questions, and that's completely fine by me if people just want to sit in on those, but you have to be there, all right? So it's kind of up to you. So if you're fine, that's great. If you're struggling with particular aspects, please come and ask me. And those office hours are there for a reason. So I basically designate a whole hour or so, and I can designate more to helping you. Just if it's not very frequented, then it's very hard for me to sit there for a whole hour, okay? So please do use those if you're struggling with different aspects of it. So today we're going to talk about the thermal properties, or measuring the thermal properties of polymers, and we're going to look at differential scanning calorimetry. Now, differential scanning calorimetry is the most frequently used technique in thermal analysis. It's used to measure the behavior of materials as a function of temperature or time. And it can be used to measure things such as melting points, crystallization behavior, and also chemical reactions. So the DSC, the basic operation of the DSC, and you'll see there's lots of different configurations of DSC available. And we'll show you kind of two configurations of this. These are the only two that I need you to know, mainly because they are the most common. So DSC essentially measures the heat flow produced in a sample when it's cooled, or held isothermically at constant temperature. So as you will see, a sample may undergo different, one or more different phase changes during heating or cooling. Let me just write this down for you. So I'm running out a little bit of space here, but so you'll see on this spreadsheet, so there was some supplementary information, but actually I've condensed it down so you can watch some videos. So there is a brief intro into DSC done by the National University of Singapore. So I've got the YouTube channel there. That's really good. There's some really good schematics in there which are worth watching. Each of these videos are probably less than 5 minutes long, so it just gives you a good brief intro. Now, we don't go through the DSC sample preparation in a lot of detail here. We'll kind of touch on it. But it's worth looking at this Mettler Toledo video, which shows you how they prepare samples to put into the DSC instrument. A lot of those samples are prepared in these aluminium crucibles. They're really small crucibles that they weigh and put the sample in. But there's lots of different crucibles available, depending on what kind of polymer you're trying to measure. So please have a look at those. It won't take much of your time to do so. So this is just to give you a general overview of the components which comprise differential scanning calorimetry instrument. So the measurements are done in an inert atmosphere. And that will be gases such as nitrogen or argon. Then you have a furnace, which heats the sample. And the reference. Now the reference used for these is normally an empty pan. So by that I mean the empty crucible. Sorry, let me write that, pan. Or a material with known thermal properties. Basically gives us some kind of baseline to compare our sample to. Now the sample generally weighs between 5 to 10 milligrams. It can be a liquid, it can be a powder, or a film. And we obviously put that into another pan. So the holding pan itself the crucible is metal. And it's metal because it has high thermal conductivity. And it's hermetically sealed. Sometimes. Sometimes it's not hermetically sealed. So you'll see in the video that they use for metal at Toledo, sometimes they put small pricks in the top of it as well, so they puncture it. Then underneath our samples, we have sensors. They've got our DSC sensors. And they hold the sample and the reference. So the sample and the reference sit directly on top of the sensors. And it records changes in power to maintain temperature. So this actual example of a DSC here is a power compensated DSC. So we'll come back to that a little bit later on. So that records. So it records changes in power to maintain temperature. And then we have a computer, which is just the processor for the whole instrument. And that controls ramp time and temperature. It uses the electrical signal from the sensors to control the sample temperature. It records the power or the temperature differences between the two different samples. And its ultimate aim is to produce thermograms which we can interpret the phase changes from. So high-end differential scanning calorimetry instrument will probably cost you in the range of about $65,000. So if you're interested in getting one, it's worth saving for. Okay, so that gives you a different idea of what they're made up of. So there are two main types of differential scanning calorimetry instruments. The first type is which we'll go through, is a power compensated, and the second is a heat flux. So the main difference is that the power compensated, the power supply remains constant, and the sample and reference are in different furnaces. So we saw that on our previous example. In the heat flux remains consistent. So that's the amount of heat put through per area. And the sample and reference are in the same surface. So it's kind of I think that's kind of the oldest version that they have. Power compensated, I think now is the most regularly used. But the power concentrator, as I said before, the sample and reference cells are heated by individual heaters, and the temperature difference between the cells is kept to near zero. And what it does is it measures the difference in power needed to maintain that temperature at zero. And that's what we use to develop our thermogram. So in the power compensated DC, the electrical power difference between the sample and the reference, which is given by the change in Q over the change in time or temperature, you can do that two different ways, is measured between the sample and the reference. And this is what a thermogram looks like for this. So it's fairly straightforward, and this is fairly consistent for any DSC measurement that you're making. So even if you change to a heat flux, this thermogram should look very similar. Moving to different instruments is not really a factor of just finding the best measurement. It's more finding the optimum instrument to measure your particular parameters. Some operate at much better higher temperatures, some at lower. So when you're trying to find an instrument, that's what you're trying to fit to there. So this is what it looks like. So we're measuring this electrical power distance on here. And then what we've got is A, and you'll see that starts to slope down. This is our TG. This is where we take our TG from. And then B is something that we call cold crystallization. So notice these are exothermic and endothermic processes. So a process where the heat flows into the sample is endothermic, and a process where the heat flows out of the sample is exothermic. Let me write that down for you. I think you should know that, but it's worth remembering because these things are all exothermic and endothermic measurements. So the TG is endothermic, the cold crystallization is exothermic, and then we have C down here, which is a TM, that's our melting temperature. And then D is actually a factor if we have crosslinks in there. And E is vaporization. So that's when we've completely decomposed our sample. So what we can see is that as we increase the temperature, we go through the first phase, which is our TG. So we go from that glassy to the rubbery state there. And then in B, we then undergo cold crystallization. Because we've got segmental mobility, we can elicit some extra crystallization in there. So they will start to fold over and find a energy favorable conformation. And then as we continue to heat, we go through the TM and we start to experience our melting temperature. Now the crosslinks are a little bit further up because we have to then these can form later on, and then as we continue to heat, we can go through vaporization. The main bit that we actually deal with is this side of things. These are the things that we're interested in. We're interested in establishing the TG, which is connected to the cold crystallization, and the TM. So measuring the TG and the TM from those things, or getting the values for those, is really straightforward. So the TG is typically reported as a midpoint value. So as we start to see a slope here, which is our TG, it will be B, which is reported as our TG value. And then TM is even easier because it's a much, as long as the polymers exhibit crystallinity, the TM is measured from point B there. So that's how they get those values. So then we have our other different type of differential scanning calorimetry called heat flux and DSC. Now, in this case, the sample and the reference are heated in the same, heated by the same heater, so they're in the same chamber. And the temperature difference between the two cells are measured. So I'm not going to go through the breakdown of those things. But the most important thing is that our sensors will sit underneath here. These are our sensors. In fact, actually, this sensor that here is actually called a star sensor. That has positions on it, as you'll see, for both the sample, which is S, and the reference. So both our crucibles can sit on top of the same thermocouple or sensor, if you like. Now, the sensor is the main component of the DSC, and it's responsible for detecting the heat flow. These are called star sensors because they have a star arrangement of thermocouples in there. So they can range from between 50 to 120 thermocouples. The higher the number of thermocouples, the greater the resolution and accuracy of the instrument. And they can operate between minus 150 degrees C to 700 degrees C, which you can appreciate is quite a wide range for a thermocouple to operate. Now, these are probably the most expensive part to replace if you have an incident in a DSC. They're around about $3,000 each to replace in there. So, and that's just because they are such a component part and they're constructed or engineered to be so specific and accurate. So the sensor properties are the most important and the most crucial part of the measurement. So if you have very high sensitivity, it makes it capable of detecting small heat flow changes. So we have an increase in our accuracy there. Also, because we increase the resolution, we can separate close line effects in polymers. So if some of the phase transitions are particularly close, that extra resolution can allow us to separate out those effects. So the other thing to touch on is the use of the crucibles at this point. So our sample pans or containers, there are lots of many different types of crucibles that you can use, and they're available really depending on the polymer or whatever sample you're trying to measure. I would say we're touching on polymers, but these can be used for other phase transition measurements, rather not exclusively for polymers. So it really depends on the application. Now, most crucibles are made of pure aluminium. Which ensures good thermal conductivity. There is about 25 different types of crucible available. So the crucibles can be hermetically sealed. We've mentioned that previously, so it's completely airtight. It can be left fully open. And it also can be covered by a pierced lid. So that's what they do in the Metal of Toledo YouTube video. But obviously the piercing in that lid determines the degree of gas exchange that is undergo with the surroundings, so it can have an influence on that. You can also have, unsurprisingly, gold crucibles. which are available for samples that react with aluminium. So there are lots of alternatives out there. So it's exactly the same plot as before, but actually in this instance, we're actually measuring a change in temperature between the two different samples there. But you can see the plot is exactly the same, and it's exactly the same for a reason. This is actually, so I'll say that these plots are all representative of PET. So that's poly. I'm going to spell this right. It's almost like the model, and it's freely available. So PET is used in a lot of plastic bottles. I think it was Mettler Toledo that did this analysis first. So a lot of the plots that you see here are taken from an analysis that they did. If you want to know the structure of that. So what linkage group is in there?
Ester.
An ester. How do we form an ester? What two functional groups do we need?
We need an alcohol and a carboxylic acid.
Good, good. So remember those things, because you'll need those things when it comes up to the exam. So we go through the same process again. We have the TG. In fact, you could do this, right? So there's a TG, TM, and the B is crystallization, cold crystallization, which we'll get back to later. D is a cross-linking. And E is a vaporization. Now, one thing you'll notice is that on this side, we have the endothermic, and this side is the exothermic. Pay attention to that, because sometimes the peaks can be flipped, and that depends how they're measuring the change, whether it's a change in the reference minus, reference minus the sample, or the sample minus the reference. But those peaks should still be in the same position as they are a function of the temperature. So those can be flipped around in some diagrams. So we've talked a little bit about crystallization in here. So as we start to heat things up, we go through the glass transition. And then what we experience is this phase called cold crystallization. And that's a process where the polymer undergoes some small amount of crystallization while heating in the DSC. So as we're getting into that rubbery state, they start to reorder and form crystalline regions. And then we actually go up to, as we continue heating, we go through the phase of TM, which is the melting temperature. Now, most of these thermograms that you will see will look the same, right? So they don't change. So just make sure that you understand where the different transitions are occurring in these thermograms. You'll notice here, this is a prime example where the endothermic is on the up. So we switch around the peaks. They're no longer negative, they're actually positive. And that's because they plotted it differently, which is a weird way around to me, but those transitions still occur at the same point. And then when we go through the cooling cycle, so we've reached about 100, it looks about 190 or just over 190 degrees C. As we start to cool things down, we can go through another crystallization step, which is called melt crystallization. Till we eventually cool our polymer right down. Now these two, the TG and the cold crystallization, are related, so I'll come back to that a little bit later on. So this is just an example specifically for PET. So as we go through that, as you start to heat, we go through the glass transition. This is the TG here. It's not very clear on here, but it's this kind of center mark on our line. Then we go through a cold crystallization phase, which happens around 185, I'm going to write that down, 0.7 degrees C. And then we go through our melting phase, which is here, which is 205.2 degrees C. So what they were able to show actually in the Metal at Toledo was that what they measured from PET and plastic bottles was very similar to the reported values. So they knew that their instrument that they were developing was working correctly based on the interpretation in there. You see a lot of these, but this is really just to get this into your head, what's going on. So again, you see it, we're going back to the normal way round, sorry, the opposite way round. We have the endothermic, we have the exothermic, so A, again, TG, B, crystallization, and C is the TM. Should have probably gave you that one to write down, but it is that simple, right? These processes are very similar for all polymers as long as they are semi-crystalline. So the TG and the TM are endothermic processes. It means that they require additional energy to increase segmental mobility and disrupt the crystal structure. So we know that because we've got to heat those things up. And for the TC, it's an exothermic process. Where the polymer chains arrange into a crystalline state. So just a reminder there that crystalline state is just when we get past the TG and we have enough segmental mobility that the polymer can rearrange to form the crystals, right? We've just got enough energy in there that they're almost fluid so they can reform these crystallization. Now the TG in relation to the crystallization is something that we can get the thermal history of a polymer from. And I'll cover that in the last two slides. But one thing that we are interested in measuring is the percentage crystallinity from these things. So the TM peak is affected by the amount of crystalline material present. This should be well understood by now by everyone. If there is crystalline regions, then it will exhibit a TM. The percentage crystallinity can be determined by comparing the area under the TM peak of a semi-crystalline polymer versus the area under a TM peak of a highly crystalline polymer. Now, these polymers are also said to be 100% crystalline. They don't always have to be polymers, but that 100% crystalline comes from one of the previous lectures where we had a good question from someone that it comes from the measurements of the X-ray diffraction. So in the X-ray diffraction, it's defined as 100% crystalline. But there's lots of different standards available for different common polymers. So we can measure the crystalline factors by looking at the enthalpy of fusion of the sample and dividing it by the enthalpy of fusion of a correspondingly highly crystalline material. So if a polymer has a TC, which is the cold crystallization curve, you'll need to subtract the area under the heat of crystallization curve to get an accurate measurement. But the area of the crystallization curve times 100% gives us the percentage crystallinity. It's pretty straightforward. We're looking at the area under the curve to calculate. Now, there is obviously different, as we said before, there is different ways of heating these polymers up. So the computer part can change the ramping and the temperatures that we get up to. So what you can see here is, again, as we, where is it, this bit here? It's not immediately evident, but there is a slight shift to the right-hand side and a higher temperature. So what is that I've just outlined there? What is this transition? Anyone, please?
Is it TG?
It's TG, good. What is this one?
Cold crystallization.
Good, good. What is this one on the end?
It's TM.
TM, good. They're all the same, all look the same, so it's pretty straightforward. So if you increase the heating rate, and you can see that this is, the top one is increased at 20 degrees C per minute, and the one at the bottom is 2.5 degrees C per minute, then the TG, you see an apparent shift in the TG, so you have an increase, apparent TG. Oop. Spell apparent right. It's not even Friday or Monday. And essentially what happens is that the change do not have enough time to rearrange at the actual TG there. And you see the same shift really occurring in that cold crystallization phase as well. Okay. So this slide illustrates the influence of the thermal history on a PET sample. So the sample was cooled under different conditions. First, it was cooled very slowly. Let's take that as number one at the bottom there. The second was actually shock cooled. This is this one at the top here. I don't know why they're in a random order. And the third was shock cooled and annealed at 65 degrees C for 10 hours. And that means that it's stored at a temperature somewhat below that of the glass transition temperature. But the heating measurements performed after each cooling run show clear differences in there. So the sample that was slowly cooled only shows a small step in TG, in glass transition, and it shows no cold crystallization period. That means that there is sufficient time available for the sample to crystallize, so the content of the amorphous material is low. The shock cooled sample shows a large glass transition step, a large TG on there. This indicates that the amorphous content of that is high. And furthermore, you see that a cold crystallization peak is observed because the sample didn't have enough time to crystallize. So if you give it sufficient amount of time upon cooling, so you cool it really slowly, you don't see that cold crystallization because it has enough time to form its crystalline regions, and the amorphous regions are lowered. When you shock cool something, so we reduce the temperature really quickly, and we will still see that cold crystallization peak occurring in there. Now, when the sample is annealed for at 65 degrees C for 10 hours, it exhibits something called enthalpy of relaxation, and that's a result of the aging process. As a result of this aging process, so that annealing process, in addition to the effects that we see because it's been shock cooled as well. So the melting peaks of the three samples are almost identical, so they do not change. So that is not influenced by any thermal pretreatment. that says pre-treatment, that says. The longer the sample is stored below the glass transition, the greater the enthalpy of relaxation. And so this peak we're looking at here. And the more pronounced the effect of physical aging. So the enthalpy of relaxation peak is often a result of the thermal history of a sample and affects the evaluation of the glass transition. So because we've stored it at 65 degrees C for 10 hours, we're now affecting the glass transition and the thermogram looks different. So the peak can be eliminated by first heating, then cooling, and then heating again. So we go through what we call a cooling heat cycle on those things. So the first thing is that the sample is heated, it's cooled, and then heated again. In this case, it's heated again at 20 Kelvin per minute. This type of measurement is often performed to thermally pre-treat the sample in a defined way in the first heating run. So as you can see, once we've done the heating, we exhibit we can see the TG, we can see the cold crystallization, and we can see the melting temperature. As we do the cooling run, we also have that melt crystallization occurring. But on the second run, we start to see that the TG has been reduced. We have no cold crystallization, and we have the TM. And that's because we've been given it sufficient time for crystallization to occur during cooling, which means we have smaller amorphous content and a higher percentage crystallinity. And as a result, we have no enthalpy of relaxation because we haven't instigated any time for aging. So we haven't put that 65 degrees C for 10 hours. It doesn't have to be 65 degrees C. Again, this is just for PET. But the main thing is that when you're annealing something or you're aging something, it has to be done below the TG and the. So the heat and cooling experiments, they eliminate the thermal history of a material, and they can be done to check the production process of a sample. So from the measure of the different crystallinity from the DC, you can get the effects of processing and aging, the effects of annealing, and you can understand you can measure the actual polymer itself with no thermal history. So freshly synthesized polymer in that case. So the main thing to take from this is that you need to just know what peaks are occurring in these. So that's the TG, where we would measure the TG from, where we're measuring the TM from, and the effects of different cooling and heating cycles on the relationship between the TG and the cold crystallization. So we have whizzed through that lecture. That is module 6 done. Next we move on to mechanical, or in the next lecture we'll move on to mechanical. I should say next lecture being Monday well, no, actually, let me work this out. If the quiz takes less than half an hour, which I think it should, the in-class assignment on Friday, then we'll be able to move on to module 7 straight away, which is good. So we're making good ground. I tried to slow things down a little bit just because of the situation we're in. But like I say, if you have any problems, please get in contact with me. But after we've done the mechanical stuff, then that will be time for your first midterm exam in there. So now is a good time. I'm giving you significant warning. Now is a good time to start to get your notes together and decide what you understand and don't understand. So that's it from me. Is there any questions? Okay, good. Well, stay safe, and then I will catch you on Friday.